All right, you guys ready?
Yeah.
All right. First one's actually a little tricky, but we might be able to get something out of it. It says, F1 is the magnitude of the force exerted by the satellite, by the Earth on a satellite in orbit, okay? So if you think about, here's the Earth, okay? Here's the Earth, and then we have a satellite in orbit over here, okay? And our satellite is in orbit, right? The natural tendency of an object in motion is to stay in motion, but in a straight line. Yes?
Yeah.
So the satellite doesn't go in a straight line, it goes around. Why does it go around?
Well, because it's always being pulled down, but it's tangential to the line.
Totally, and those things kind of have this nice kind of balancing, not in a balance in a force kind of way, but in like a delicate balance.
Yeah.
So, what Gru is implying is there has to be some force, right? And you need a central force if you're going in a circle. True?
Yeah.
All right, so it says if F1 is the magnitude of the force exerted by the Earth on the satellite. Got it? All right, and F2 is the magnitude of the force exerted by the satellite back on the Earth, which is true. So we're going to compare F of the Earth on the satellite to the force of the satellite on the Earth. Which is greater?
Well, wouldn't it have the satellite can't exert force, can it? So it has to be the Earth is greater than the satellite, rather than the force by the satellite.
Boy, you would totally think so, except for...
Oh man, that was totally wrong.
N3FLP.
No. It's got to be $1 right there.
Oh, that's a... Okay, so the force of the Earth on the satellite and the force of the satellite on the Earth. What has to be true about those? They have to be
That'd be equal.
equal in strength, opposite in direction, and act on the other object. Right?
Yeah.
Now, but here's the deal. Like, we're tricked into thinking, oh, well, the force over the Earth is much bigger, right? Because the satellite is so small. But we're going to see in a moment why they're the same. But I think that as long as you have this framework for understanding how the forces are, right? The question is then, this is the real question, is if the force is the same, why is the satellite going around the Earth and not the Earth going around the satellite? That's the real question, right? So why is that?
The mass.
That's right. So the satellite has a small mass and a big acceleration, right? But what does the Earth have?
Big, small.
A huge mass, and it's that little dot is the acceleration.
Okay.
Is that cool? Now, what this does though is this actually can answer a real question. Is, well, what if we start making the mass bigger and bigger and bigger of the satellite? What if it's the mass of the moon?
Yeah.
Right? Then does the moon actually exert a significant force on the Earth? And the answer is it really does. It really does. And I think if you were able to look at the orbit of the Earth as the moon goes around, I think you would see it shift a little and then shift a little back. You get a wobble of the Earth as the moon goes around because the moon really is pulling it.
Yeah.
This actually is very cool because this is one of the ways that astronauts found exoplanets. So the first way that astronauts found exoplanets are planets outside our solar system, is they're like, let's just look at this star for a long time, and hopefully a planet will pass in front of it, and it'll dim, and then it'll brighten again, and we'll be like, a planet just moved in front.
Yeah.
So they did this, and they found some, and they're like, oh my gosh, look, that's so cool. But I'm thinking, like, you gotta be looking on the plane of the orbit,
Yeah.
right?
Yeah.
Like, what are the chances of that?
Yeah.
So then they said, well, let's do it a different way. Let's watch it. We're going to watch this star relative to the background stars. And if we see it move this way and then move back, we're going to know that there's a planet orbiting it that's large enough to cause it to wobble. That's another way that they can find exoplanets. Cool?
Yeah.
Fantastic. How do you feel about that?
Pretty good.
Oof. A newly discovered planet has twice the mass of the Earth, but the acceleration due to gravity on the new planet's surface is exactly the same. Oh my gosh. All right, so here's one of the things that we know. If you want to calculate the acceleration due to gravity, which is the same thing as the gravitational field strength, we use baby g for that. What's the value on the surface of the Earth?
9.8.
We're going to go with 10 because it's easier to, okay? We know it's 10. To calculate it, we need to know three things. We need to know this big G. This big G is the universal gravitational constant, and its number is 6.67 times 10 to the negative 11.
It's a nice little round number.
So it's a very, very, I mean, you'll notice it's a very small number,
Yeah.
right? Can you notice it's a really small number?
Mm-hmm.
And what that means is that the masses that are, in order to exert a reasonable force, you need to have a huge mass. You need to be a planet or a moon,
Yeah.
right? There's a great movie in the late 90s, early 2000s called Armageddon.
Yep.
So they're gonna land on an asteroid and then drill and bury a thermonuclear weapon so they can blow it apart. It's gonna hit the Earth. And they're like, okay, we're gonna land you on here, right? But there's not enough mass to have enough gravity, right, for it to hold you down. So we're gonna put these reverse jetpacks on you that are gonna shoot gas upward, right? Because if they shoot the gas upward, the gas is gonna then push you downward so that it feels like Earth's gravity. I was like, this is a great cheat. I love this, right? This is such a great cheat. So this constant allows us to use mass in kilograms, distances in meters.
Okay.
Is that cool?
Yeah.
It's universal. It's the same. We think it's the same everywhere in the universe. It's a huge deal. It's on the equation sheet. Okay?
Big one.
Okay. So the other thing you need to know is the mass of the planet in question and then the radius of the planet in question and its squared. So this is something that you need to memorize. It's not on the equation sheet. Okay? This is something that you need to memorize and come armed with. Cool? Dude, what is up?
What's up, Paige?
Now I'll show you where this comes from in a moment, but let's work through the problem real quick. So let's write it for Earth. Okay, let's write it for Earth. So the G value on the Earth is equal to big G times the mass of the Earth over the radius of the Earth squared. Is that cool?
Yeah.
So let's do it for the new planet. The new planet says what? It has twice the mass of the Earth. So the G on the new planet is equal to capital G, universal gravitational constant, times the mass of the new planet divided by the radius of the new planet squared. Is that cool? You guys feel me on that? So I like to just write them each, and then we can kind of like massage this one and see where it goes. What does it tell me?
Well, you know that Mn is equal to 2me,
And
and that I'm assuming Ge is equal to Gn.
dude, you showed up to play today, okay? So Drew is right on the money here. He's like, this is exactly where we are, right? So let me substitute those in here. So basically I'm saying that I have GE, right, is equal to G, oh gosh. My brain stopped working there for a second. 2me over the radius of the new planet squared. Is that cool?
GE or GN?
So it's both because, dude,
Hello, everybody.
what is up? What do we got? What do we?
That's up to them.
Well, it's like chicken fajitas, but they're not seasoned well. So they put a little jelly on a taco. Fantastic. Jelly salsa, even better. We don't have time for that.
So what we have, okay, so since this is GE and this is GE, right,
Yeah.
I could basically just set these two things equal to each other.
Yeah.
Because I need to know the radius, because it says the radius of the new planet in terms of the radius of Earth. So I need to get an expression that says Rn in terms of Re.
Yeah.
Does that make sense? So this is GE, this is GE. So now I'm going to set them equal to each other. So I have G times the mass of the Earth all over the radius of the Earth squared is equal to G times 2 times the mass of the Earth all over the radius of the new planet squared. Is that cool? And now some fun stuff happens, right? Basically we have this and this, yeah?
Yeah.
So I'm gonna just flip this over here, so I have the radius of the new planet squared is equal to 2 times the radius of the Earth squared. You guys see how I solved that?
Yeah.
So a lot of times, once you get the conceptual framework, it becomes an algebra problem, and that's sometimes where we stumble too, but, all right, so now what do I have to do to both sides?
Square root.
So the radius of the new planet is equal to root 2 times the radius of the Earth. Look at it, okay? More clear or less clear? Okay, is that consistent with the way that you feel like approaching this?
Yeah.
Okay, all right, I love it, let's keep going.
Mr. Pat, I have a quick question about one of the worksheets. It's like a small question.
Go ahead.
On the 2014 one, I was confused on why, that in the solution, only the mass of the disk was included in the.
Uh-oh. Dave, you're gonna make me question my whole existence here.
That's what we're doing.
Listen, there's something about this class that I just want to make sure that you guys know is it's hard, right? There are some hard moments in this class, right? But you guys are gonna go to college, and your first couple semesters, you're gonna be like, why is everybody here so dumb? Because you guys go to a great high school with great teachers. The problem is you don't know how good your teachers are because you're comparing them to each other. Even the bad teachers here are still good teachers, okay? All right? And so you're gonna go to school, and I don't care where you go, unless you're going to Harvard, okay, right? You're gonna look around and be like, what the hell is happening with these people? And that's because you just had great experiences, but you're gonna then get into some hard classes, right? Drew, are you gonna study engineering?
Yes, sir.
Yeah, you're gonna get into engineering and be like, oh, this is a breeze. They're gonna get into engineering too. Like, this class is terrible. I don't want that to be the first time you had a hard class, right? I don't want you to get in there and be like, I don't know how to do with any of this stuff. I want you to get in there and go, this is hard, but I've done hard before. Let's just go on.
Yeah, I was talking to the space physics professor at a school I was touring, and he's like, he asked what class I was in. I was like, yeah, I'm in AP Physics, C Mechanics. He goes, oh, the good one.
Yeah, aren't the others like algebra?
What year is that?
2014.
Oh, Charles.
What's up there, man? Do you guys have the 2014?
Yeah.
Let's look at it real quick. Okay, let's look at it real quick. We'll get back to the gravitation.
Dave, is that at 2014, number 3?
Yeah.
So let me see what that. I'm assuming those are.
All right. Oh my gosh, what am I doing over here? I'm being an idiot. Stop being an idiot. Okay, here we go. Sorry for the delay. Now, we're going to assume that I have done the key correctly, but okay. So let's look at the problem. The problem said, why do I have it twice? Did I open it twice? Okay, it says, bloop, bloop. Okay, a large circular disk of mass m and radius r is initially stationary on a horizontal icy surface. Ooh, you think that's important?
Yes.
Right? Okay. A person of mass m over 2 stands on the edge of the disk. Without slipping on the disk, the person throws a large stone of mass m over 20 horizontally with an initial, okay, so how's he throw it? Oh my god, that's gonna be a problem. Horizontally with an initial speed of v0 from a height h above the ice. Okay. As shown in the figure, the coefficient of friction between the disk and the ice is mu. Okay. All velocities are measured relative to the ground. The time it takes to throw the stone is negligible. Express all algebraic answers in terms of stuff. Derive an expression for the length of time it will take the stone to strike the ice. Okay. We can do that. Can I, no? Why? Why doesn't that like this? Why? It's like pan. Will that help? I don't think. Okay. Doesn't matter. Okay. So here's the key. This is the college board key, not my key. Okay. So it says we're gonna get A is worth 2 points. Okay. For using kinematic expressions for the vertical motion. So it says y minus y0, which is your delta y, right? That's your change in your height, is equal to 1/2 at squared plus v0t. Is that cool? Now here's the thing. What's the change in the y position? It's the height. Why does it have 0 here for my v1t?
Because it's a rest, right?
Vertical,
Which way did you throw it?
horizontal.
Horizontally. So what's the initial vertical velocity?
0.
0. That's why there's a 0 for the v here. Is that cool? So if I want to solve for t, all right, I'm going to multiply both sides by 2, divide both sides by g, and take the square root, 2h over g. Is that cool?
Yeah.
Okay. Let's see what B says. B says, assuming that the disk is free to slide on the ice, derive an expression for the speed of the disk and person immediately after the stone is thrown. Now, if I said that the person catches the stone, you might think, oh, that's a collision problem. But if I say the person throws the stone, is that a reverse collision? It's an explosion. So what does that tell me? What kind of problem is this then? If I told you it was a collision problem, you would tell me it's momentum. If I tell you an explosion, it's still momentum. So can we use our conservation of momentum concept to go do this problem?
Yeah.
Okay, let's check and see what they did. So we got 3 points. Okay. Now here's what I like. Your goal is not to get every answer right. Your goal is to accrue as many points as you can. This is a 3-pointer. Guess what you get 1 point for?
Just the
Right? At the beginning of the year, you guys were crying because I'm like, oh my God, what am I going to show all my work? This is why. This is literally why. Because you're just trying to get as many points as you can, man. You know it's a momentum problem. Pi is equal to PF. Okay? And then, for substituting the momentum of the stone into the correct expression and for substituting the momentum of the person disk into the system, what's your initial momentum? 0. So then you have m1v1 plus m2v2, right? The stone is m over 20 with speed v0. And then what is the mass of the disk in person system? It's m plus m over 2v. And then you just solve. Cool? Right? It's so easy when they do it. So easy when they do it.
See, when I first did it, I saw initial velocity, so I thought the initial situation had momentum.
Yeah, so the person is standing on the disc and throws it. If you throw it, what are you going to do? You're going to go back. You ever thrown a medicine ball at the gym?
Yeah.
These heavy balls, right? If you do like CrossFit, they like bounce them on the ground or like throw them against the wall. Or those are crazy people. Don't do that. The CrossFit people, they're militant and you can get really like ripped, but they're injury prone.
Oh, yeah.
Yeah,
Like that's the real problem.
Seen
It's
those
not super
CrossFit
healthy.
pull-ups.
It's not super healthy.
PF.
I'm don't get me wrong, those people are strong, but I mean you get like end up with a lot of surgeries. Anyway, when you throw that, you really have to do this thing with your feet where you gotta like do this because when you throw the ball, whatever force you put on that ball, it's gonna push the same force back on you. That's a Newton's third law of force pair. So you have to have a lot of friction with the ground in order to do that. If you try to do this on like roller skates and you threw this, you'd go backward. Now, honestly, If you do this, what happens is if there's friction between your feet and the ground, you're going to rotate back with the pivot point at the friction. So anyway, so the speed of the disc person is negative 1/30, and it says here because it asks for the speed, negative sign doesn't matter.
Oh,
Cool? All right. C says, derive an expression for the time it'll take for the disc to stop sliding. Now, there's two ways to do this. You could consider this as a kinematics problem where you'd have to draw the force diagram, figure out the acceleration via the force diagram, and then use a kinematic expression for the time. Or for the, oh yeah, actually that's the only way you can do it because it wants to know the time it'll take. If you want to know the distance, you could use energy, but because it wants to know the time, I think you're stuck with kinematics. Is that cool? Derive an expression for the time it will take for the disc to stop sliding. Okay, what does it say? Okay. Here we go. So if we're using a correct expression for Newton's second law, so if you go with F equals ma, all right, but what it's saying here is what force is the unbalanced force as the disc starts sliding?
For frictional force.
It's the friction. So they have this little F for friction is equal to ma. Is that cool? And then what do we know about the frictional force? What's it equal to? Mu mg. So mu mg is equal to ma. You see they made a little substitution there. So how do you express the acceleration? A is equal to mu g because the mass cancels on both sides. Yeah.
So, I was confused on why the frictional force wouldn't be the mg plus the normal force because the guy is still standing up.
So this m that they're talking about here is both the mass of the guy and the disc.
Oh,
They don't explicitly say it here, nor do I explicitly say it there. And I think because I knew the m was going to cancel. But in a very realistic sense, this m that they're talking about here is, basically it's the m plus m over 2, because it's the mass of the disc plus the mass of the guy.
I made it 3m/2.
Yes, but even if you made it 3m over 2 here and 3m over 2 here, they're going to cancel. Is that cool?
Yeah.
You guys, I mean, you notice that as a deal? So that's the thing. So now that I have my acceleration, I'm going to put it into here. Now there's an issue here. Okay, there's an issue here we're gonna have to talk about. For correctly substituting, so the velocity of the disc and the person, right? They need to slide to a stop. So what's the final velocity? 0. What's the initial velocity of the disc and the person?
The previous.
Yeah.
It's the answer to the previous problem. You see that? Does that make sense?
So if you get the incorrect, if you say you got A wrong, and you substituted correctly for C, and you still get all 3 of those points, right?
Yes, so if you get this answer wrong, but you carry it down here, you could totally get this whole thing right.
That's why the bridge fell down.
Now, here's a funny thing, right? So what we're saying is, which way is he throwing it? He throws it this way, true? So we have a negative, the velocity of the velocity of the stone is that way. So what direction is the initial velocity? It's to the left. That's why they have the negative here. But if the velocity of the guy and the disc is to the left, what direction is the acceleration? It's to the right because it's slowing him down. They have to be opposite. That's why you have a negative sign here and a positive sign here. Oh, look at that. Now it's going to let me write. What happened? I'm very upset now. It's fine. It's fine. It's fine. You guys with me on that? Is that cool?
Yeah.
Okay, so there's the time. Sound good?
Wait, so V1 is at what point?
So V1 is after the guy throws the ball, he and the guy in the disc start moving backward.
Yeah.
That's V1.
Okay.
Cool? All right, let's keep going since we're having so much fun. I mean, I'm having fun. I don't know if you guys are having fun. The person now stands on a similar disc. Oh, this is a big deal.
Yeah.
Okay. Are we throwing things? What are we doing?
Rolled off my desk.
A similar disc of mass M and radius R that's fixed fixed pole through the center so that it can only rotate on the ice. That's going to be a big deal. Person throws the same stone horizontally in a tangential direction. So this is cool because if he throws it this way, what's going to happen to my disc? It's going to start spinning. Does that make sense?
Yeah.
Okay. The person throws the same stone horizontally tangentially with a speed v0 as shown in the figure. The rotational inertia of the disc is? No, so why does this one and not? Okay, I can't even right now. Okay. Derive an expression for the angular speed omega of the disc immediately after the stone is thrown. I think this is another momentum problem. What kind of momentum is this? This is angular momentum, right?
Yeah.
All right, but is angular momentum still conserved?
Yes.
Yes, it is. Let's see what they did. Guess what you get a point for? Yeah, so L is the angular momentum. So if you set the initial angular momentum equal to the final angular momentum, boom, you're good to go. Now, something that we talked about, and I want to make sure that we remember, is that L is equal to R cross P for a point for a point particle, right? For a point particle, it's equal to R cross P. Now, what is P?
Or linear one?
So RMV.
Yeah.
Is that cool? So if I look at the situation, here's the disk, here's my R vector here, right? What weighs the V vector?
Tangential.
It's there. So what do you notice about R and V?
They're 90 degrees.
They're perpendicular. So because this is a cross product, this is actually RMV sine theta, right?
Yeah.
Because it's 90, it's one, right?
Exactamundo. Okay? Did you guys hear that? So because if you notice there's 90 degrees, so what do they say? They're like, oh, well, they're like, L is equal to MRV. It is equal to MRV, but like it's not obvious, that's not necessarily obvious why it's equal to MRV. But because it's a point particle, we're going to use that. But what about the whole disk? The disk is a rigid object that's free to rotate. So how do we say the angular momentum for a rigid object? Well, if we use our framework that linear momentum is mv, then what is angular momentum?
I.
It's I omega, right? It's I wumbo. Is that
Go
cool?
off to college and just, my professor's gonna write that up there, and like, wumbo.
Wumbo. So that's why that says for rotation it's there. Is that cool? So, sorry. So it says, if you tell me that they're equal, for substituting the angular momentum of the stone into the correct expression for conservation of angular momentum. So the stone is the point particle. So it's M stone, R stone, V stone. Is that cool? All right. And then for the substituting the correct angular momentum for the person into the correct expression for the angular momentum. All right. So there actually, it's fine here. They said I for the person, omega for the person. Is that cool? And then for the disk, it's I omega for the disk. Cool? So when we move this one down here, what's the mass of the stone?
Over 20.
It's M over 20 times R V0, because that's the speed at which you throw it. Okay? Now this is, I don't really like this. I don't like the fact they put a negative here. Really, you just add these things together, but they know that like, well, this is rotating in one way and the other stuff is rotating in the other way. It's totally fine. If you think about this disc, the stone is gonna go in the positive direction and the guy and the disc are gonna go in the negative direction. Does that make sense? So if you add it all up, it has to be equal to 0.
Yeah.
Now, whether you add them all up and then subtract on this side and you end up knowing they're negative, or you just hedge and say they're negative to begin with, it doesn't really matter. Okay. So for the disk, what is the rotational inertia of the disk? It's mr squared over 2 times its omega, which is omega. And for the guy, right? So if we're using the guy as a point particle, the person,
Yeah.
right? The rotational inertia of a person, a point particle, is mr squared. But what is the mass of the person? M over 2. So that's how they got that there. So the idea of this problem is to realize that it's, again, another momentum question. A pirate went to the doctor to have a look at some moles on his back. After the inspection, the doctor told him, "No need to worry, they're benign." The pirate replied, you better look again, Doc. I think thar be 10.
What?
That's terrible. What? Why? It's my nerdy physics teacher friends. Terrible. I mean, like, terrible, terrible. Are you serious? Sorry. Okay. We're gonna see if
What's
it
up,
records.
Keegan?
We're gonna see if it records. And then the person now stands on the disc at rest, r over 2. So the person is going to move over here to r over 2 from the center. The person now throws the stone horizontally with speed v in the same direction. Is the angular speed of the disc immediately after throwing the stone from the new position greater than, less than, or equal to the old one? What do you think? What's your gut tell you?
Probably the same.
I'm just saying, right, isn't momentum's conserved.
Sure, momentum is conserved, but one of the parts of the momentum was the momentum of the thing that you threw, right?
Yeah.
It wasn't the momentum equal to mRV, doesn't the R matter?
R is less.
Yeah.
Yeah.
Small zero.
So let's see what they said.
Oh, wow, that's.
Okay, so it's less than, okay? Because what we know is the angular momentum of the stone ends up having to be equal to the angular momentum of the disc in person, right? And if you're less far from the center, then the angular momentum that you give the stone actually has to be less, doesn't it?
Yeah.
Okay, think about it this way. What if you were at the center and you threw it? What would the angular velocity, what would the angular velocity be then?
None.
0, because it wouldn't turn at all. So I think it has to decrease as you get closer to the center. Okay. All right.
Oh, that makes sense.
Yeah, it makes a little bit
It's
sense.
like, it's kind of like a door.
Yes.
I'm pulling down the center.
No, I know. Oh, I see this one, he says he stands for the same.
What's up?
The arm over 2, so have it be
The sine theta doesn't have to be the answer of part D, because the angle is 90, right?
Yes, that's correct. So when we look at this here, okay, when we look at this whole problem, again, no one's expecting you to get all the points, right? You may be on this one and be like, is this a number 3? Yeah, you may just be out of time. You may not get to D and E on this one. You just might be out of time. Or you might be like, I'm really feeling good about A, B, C, right?
Yeah.
I maybe get, I don't really wanna mess with this, this looks a little hard, let me go back and see if I can get a point for another one, right? We're not trying to get everything right, and you don't have to grind it out, you don't have infinite time.
Would you go through and just make sure that anytime they're mentioning like angular momentum or energy or things like that, you're just throwing on those so that you can get that free point for each
Absolutely.
statement?
I mean, and that's why, and this is one of the things that Nico said true,
I'm
is
gonna write P equals PM. I like it. I'll
Don't-
put everything there.
don't leave any force diagrams blank,
Oh,
Yeah,
yeah,
it's like-
it's a big one.
right? Make sure if you have a sense that it's a momentum problem, say initial momentum equals final momentum, and try to like grind out the second line also, right? So you can say like, I know momentum is constant, or the, right? Right? You're gonna get this. There's a point. If you can get to like here, maybe you can get 2, right?
Yeah.
So yeah. So try to identify what kind of problem you think it is. Is it a kinematics problem? Is it a momentum problem? Is it an energy problem? Is it a rotation problem? And then go from there.
For when you substitute back in for C, would you have to know what the sign is from B? Because since they mentioned like, because they're asking for speed in B, but if you're
Yeah,
in
so
C.
what you need, okay, what you need is you need to know that whatever direction the initial velocity was, the acceleration is in the opposite direction. If you don't do that, right, if you somehow made both of these positive, if you made both these positive, you're gonna end up with a negative sign on your time.
So it's pretty easy to figure out.
Yeah, if you're like, why is my time negative? Because right, because if you had if this was positive and you added it to both or subtracted from both sides, you'd end up with a negative time, and that doesn't make any sense. All right, they don't go through and check every one of your work. If you're like, I got negative time, let's just make it positive and hope for the best. That's a reasonable strategy. Cool? How do you feel about this whole problem? Better? Okay.
So for part D, this zone also has angular momentum.
Yeah, so this is an interesting idea here. Okay, this is a very interesting idea. So a point particle, right? A point particle can have rotational or can have angular momentum even though it's going straight.
Okay.
So if you think about this stone here, it was V, right? And it's
Yeah.
moving in this direction at a constant speed, right? It's going this way. If you talk about it relative to point P here, it's not exactly in rotational motion around it, but you can see that it's moving, and we can talk about its angular momentum. We can talk about its angular momentum as it goes.
Yeah.
And if you want to talk about the angular momentum for a linear particle, it's R cross P.
Okay.
Is that cool?
Yeah.
All right? You guys want to go back to that gravitation?
Yeah.
Is that all right? Two. Are we on 3? Oh, my gosh.
That'd be so funny.
A small mass is released from rest from a very great distance from a larger stationary mass. Which of the following graph best represents the potential energy of the system of the two mass system as a function of time? You know, you need to do this one. You need to know the definition.
Yeah.
All right. You guys have an equation sheet?
Yeah.
Me? I haven't done it. I think you're old. I do it too much.
This one, I put B. Or, I put E.
I put it.
It's like you know, like I'm always missing.
All right. So find the equation for gravitational potential energy, but we need it.
Yeah, in terms of big G.
Right, we need it in terms of universal gravitation. Okay, can you find it? It should be on there.
Negative change in, oh, you want me to say it?
Well, hold on, let's find it. Did you find it?
Hang on.
The change in UG, is that what you're?
Change in UG is
negative
G
G
change
M
in
one,
H, right?
No, so we need the gravitational one.
UG.
Oh, so big UG is negative G M1 times MT2 over R.
Oh, I see that.
Yeah,
So it's
yeah.
the last one, right?
Now, we talked a lot about this, but what's the deal with this? The thing that you have to notice is it's negative.
Okay.
Yep.
It's negative. Okay? So it says that my object, a small mass, we'll put it out here, is released from rest from some great distance of what? Some large mass. So if the distance is great, what does that tell you about your R value?
It's really.
It's great. So what does that tell you about the whole side here then?
Small.
It's zero, like basically zero, true?
Yeah.
All right, and as your R gets bigger, right? I'm sorry, as your R gets smaller, the whole side gets bigger but negative. So it can't be this one, why?
Positive.
Value's positive. It could be this one, right? Could it be this one? No. Could it be this one?
No.
No, not really, right? That doesn't make, so we have it narrowed down to 2. Okay? We have it narrowed down to 2. It might be this one. And it might be this one. Okay? How do we know which one it is?
What is proportional to?
I mean, is it a linear relationship between the time and the potential energy? Or is it like this looks like some sort of curve, maybe a parabolic something?
The top never changes, does it?
What's that?
But like the top value never changes.
The top value never changes.
If you just get incrementally the same, but smaller, shouldn't be constant?
Yeah.
There's no like exponential square or
Isn't
anything
it?
like that.
I don't know.
Accelerating.
Cause I think it's the curve.
Yeah, cause if you're getting closer, don't you have a larger acceleration?
You have something over a variable.
Well, I think that if we conceptualize this, is it moving in here at a constant speed? No. What's happening to it?
Accelerating.
It's getting faster and faster and faster. So I think the rate at which the potential energy is changing is going to be increasing. So I think it's not this one. I think it's this one. Cool?
Yeah.
Yeah. Interesting though, right? Because now what we have is, oh, this might be something we need to know.
Seems helpful.
Ooh,
Yeah.
I like this one. A satellite, S, is an elliptical orbit around a planet P as shown, with radius R1 and R2 being its closest and farthest distance, respectively. If the satellite has a speed of V1 at its closest distance, what's the farthest distance? We literally just talked about this the other day.
Yeah, you look at the diagram.
Okay? What's that?
The diagram.
Oh, now I remember. Okay.
This is specifically an angular momentum problem. Okay? What do we know about angular momentum? So, L1 is equal to L2, not Li, dumbass. There you go. All right, now, at this moment in time, at this moment here, and at this moment here, right? We know the angular momentum, they're point particles, yes?
Yeah.
They're point particles in linear motion. So I have R cross P, so R1 P1 is equal to R2 P2 cross. Is that cool? Feel good about that?
Yeah.
Now, what I like about this is if we do this RMV, R1 M1 V1 is equal to R2 M2 V2. Do I need the sine theta?
No, because if you look, your V is like at 90 degrees to your,
Dudes.
radius.
How cool is that?
Pretty cool.
So now, oh, what do you know about M1 and M2?
I can't say.
So I have R1 V1 is equal to R2 V2. So if I solve for V2, it's equal to R1 V1 divided by R2, and Bob's your uncle. Cool?
Yeah.
This problem that asks you how many times faster it is when it's close versus far away is specifically an angular momentum problem. Kepler figured this out in the 1600s. What do you guys do with your lives? Just kidding. Just kidding.
Not
Yeah.
bad.
Can I please borrow a computer?
Of course, of course, of course, of course. Yes. Help yourself, son. Help yourself.
I guess I don't realize the applications, because when I think momentum, I always think of something colliding.
Absolutely, right? I will tell you though, isn't this really a collision problem? And the angular momentum is a little bit different, but
Probably more valid.
yeah.
Yeah.
Cool?
No, probably it is.
Guys like that one? Yeah. If you see this problem on the test, you'll be like, oh my gosh. You're gonna be very excited.
Gonna get solved.
Ooh. A satellite travels around an elliptical orbit as shown. The satellite moves from X to Y. Which of the following is true about its speed and angular momentum? Psh. So as it travels from X to Y, what happens to its speed? Increase or decrease? It increases, right? We know the closer it is, the faster it's going. Farther away it is, the slower it's going. So it's going from X to Y, okay? So speed increases, but what did we just decide about angular momentum? It totally stays the same. All right, so I need speed increases and angular momentum stays the same.
Got it.
There you go. There it is. Cool? Right? And it wasn't easy a minute ago, but now you're like, oh yeah, totally. Again, you guys really want to know what Kepler decided? It's like the coolest thing ever. When you look at an elliptical orbit, okay, so planets orbit stars in elliptical orbits. Is that cool? And what he actually discovered, which is pretty much the coolest thing ever, is the star in question is going to be at one of the two focal points of your ellipse.
Yeah.
Is that all right?
Yeah.
And what he found out, and this is just, there's just people, right? There's people through history who thought differently than the rest of us, right? And that's fine. That's why stuff got invented, right? And we have laws of nature. He said, take your planet and put it somewhere on here. Draw a line from the planet to the star and let this line trace out an area in a given period of time. So if I color in my area here, okay? Now, this happened in time t, okay? This happened in time t. If I look at my planet over here, and I start watching it at time t, it's going a lot faster over here, true? So the distance it travels is much farther. Let's say it travels this far in time t. But guess what? If I take this line and I trace out the area, if I shade the area that this line creates here, guess what's true about those two areas? Yeah, dudes, it's equal areas in equal times. How amazing is that as an idea? Like, that is sick. Like, how did you get that from watching Mars for like 3 years? Like, there's just no way. There's just no way. They didn't have telescopes. He just goes out and he's like, well, there's Mars again. I'm not enthusiastic about it. Ooh, a newly discovered planet called Cosmo has 4 times the mass of the Earth. The radius of the Earth is RE. The gravitational field strength is equal to that of the surface of the Earth. Oh, we already did this problem. Right? We did this, not this exact problem, but you don't like that one?
Oh no, I logged in, everything booted up.
And it was on low battery.
I'm so sorry. Okay, so we can skip it. Oh, I like this one already. 2 artificial satellites, 1 and 2, orbit the Earth in circular orbits having radii R1 and R2 respectively. It turns out that R2 is 2R1. The acceleration A2 and A1 of the satellites are related by which of the following? So here's the deal. If you look at the surface of the Earth, right? All right, what's our G value at the surface? It's about 10 meters per second squared, or 10 newtons per kilogram. True? But the thing is, though, that the gravitational field strength, as we saw earlier, can be calculated by universal gravitational constant, mass of the planet, times radius squared. Now, if you're at the surface of the planet, that's the radius of the planet. But this actually extends out from the center to anywhere on the planet. And you'll notice that R1 is drawn from the center and R2 is also drawn from the center. Does that make sense? So let's do the G values for each and see how they compare. So the G value for 1 is equal to GM over R1 squared. Is that cool? What is G at 2? GM over what? 2R1 what? Squared. See how sneaky they're being here? Now what I like about this, okay, what I like about this is I'm gonna massage it a little bit, and I have GM over 4R1.
Squared.
Squared, thank you. Is that cool? Now, this is the part that I want you to notice because it's not obvious what I'm gonna do here. It'll be obvious once you see me do it, but it's not obvious to know what to do here. Do you see I have a value for G1 right here?
Yeah.
It's GM over R1 squared. Do you see that here?
Yes.
Yeah.
So what I then do is I'm gonna say, oh, well, what is G2 then? Well, what I have is you'll notice, you see I have GM, you see it right there?
Yeah.
Do you see how that's G1? So basically what I have then is I have does that make some sense? So when they ask you to compare things, oftentimes it's nice to be able to say, oh, I can see the thing I have here. I'm going to make a bulk substitution. And I have 1/4.
Was it okay to think of this like inverse squared?
Yes. Yes. So Charles used a reasoning idea. He said, look, if I know that I'm twice as far away, what kind of relationship do I have here? It's an inverse square relationship. So if I double my radius, what happens to my gravitational field strength? Goes down by a factor 4. Talk about the butter gun. Did we talk about the butter gun?
Yes.
I thought we did, right? I'm sorry, guys. Butter gun. The butter gun.
You missed it.
Just some shenanigans happened when you guys were gone.
Yeah.
This was not good. It was not my best teaching, but. All right. Are we still good? You gonna keep going? You guys you need a brain break? Too bad. Suck it up. I'm kidding. I'm kidding.
You can get a butter gun for $156 on eBay.
So glad.
Wish my test there.
Okay, this is a reasoning problem.
Do we even have a pick today?
20 minutes.
Oh, gosh.
Are any of you guys shooting each other with water? Apparently it's a big deal.
I got-
tons
I
of
got-
stuff in my car.
You're out?
I got it last night.
I saw.
I know.
Oh, Ava told me that, like, she's like, he's very fast. I was like, I know. I go, I can't believe you caught him.
Almost like
They did have a car. I think that didn't help me.
Where did they get?
Are you playing?
I was just
Yeah.
Do people know you're here?
Yeah, but I don't know if they can get you on school grounds.
They can't, you can't do
Yeah,
it on
that's
school
not
grounds,
public
it's
building.
qualified.
Yes.
But it's not school grounds during school, though.
Oh, it's
No,
Listen,
no.
when we
80
leave,
blocks, 305.
Oh, I have, there are 360s. We have each other's like locations, so. They see down, what do you, walk out in a huddle or something?
Yeah, let's make sure that you're,
We're good.
You might wanna be ready.
I would.
I forgot, I have life jacket in the car, I have water balloons in a bus like next to my center console.
You should have
And the squirt gun in the back with 3 water bottles,
I had
perfect
it.
water ratio.
Oh, nice.
And just
I
low.
was doing it, man.
They were missing that long.
It was a while, yeah.
You could just check Brendan, I think it's waiting for you or something.
okay. The radius of the Earth is approximately 6,000 kilometers.
Is that factual? Or?
Yes.
Oh, okay, good to know.
Okay. So this is 6,000. Okay. The acceleration of an astronaut in perfectly circular orbit 300 kilometers above the surface. Now, 300 kilometers compared to 6,000 kilometers.
Not very much.
That's not
The 120.
Like if you think 600 kilometers would be a tenth, right?
Yeah.
Right?
Yeah.
So this is what, 1/20th? 5%? So where is it then?
6,300.
It's there. Is that cool? Is that far off the surface? No, it's not. This is not a calculation problem. This is a use your brain problem. At 6,000 kilometers, here, what is our G value?
About 9.8.
That's about 10, right?
Yeah.
So what do you think it is there?
Somewhere around 9.
Oh,
That's easy.
That was my reasoning.
why?
I didn't know if that was the right way to think.
That's right. That's exactly
Why
right.
did I pick 11?
You're going the wrong way.
You're going the wrong way.
Yes, as R goes up, but this is such a small incremental change. But this then begs the question is like, well, if the gravitational field strength isn't much less, then why do astronauts look like they're weightless in the International Space Station?
They're in constant free fall.
Because as it goes around, they're always falling straight down, right?
How'd you know that?
They're always falling straight down. But even though they're falling straight down, they're going sideways enough to always fall around the Earth. So they're falling, and the thing that they're in is also falling out from underneath them. So it's like if you're in an elevator and someone cuts the cable, you're falling and the elevator's falling. You look like you're floating inside there, even though you're in a large gravitational field.
That's freaky. You know,
Right?
You're having that constant like free fall feeling in your gut.
So this is one of the things that astronauts battle against all the time, is they always feel, right? Because right now you're just standing and your organs are neatly stacked on one another and you are comfortable with that feeling.
Sure.
If you're in constant free fall, your organs are like moving around inside your chest cavity. That seems weird, right?
Imagine how bad their sleep is after the first few minutes or something.
Oh, I wouldn't do that.
Spain, their spines gotta be struggling
I
out
don't think
there.
it created like artificial. Imagine going from there back to Earth.
Why don't they start
But like, you're like, what, 5, 7, come back 6
Yeah.
foot, but you're like
Yeah, why don't they start
Did you
spinning?
get shorter or taller?
What do you mean?
Like at night, why don't they just start spinning to create some gravity against like the outside of the thing?
So the thing isn't wide enough that it makes a difference. Right.
Really spin.
Yeah. So and the spinning just compounds your problem.
Yeah,
I'm sure,
You're like
Right.
longer, I guess. So it's all.
All right, you ready? So it says a satellite. Can I move this? Can I make it smaller?
No, it's gonna be like 8 months.
I don't think I can. Can I make it smaller? Can I?
9 months.
That's
One
a lot.
week trip.
That's crazy.
You were like almost right on the money.
I think actually.
Oh no! Now I broke it.
I don't think like, I don't wanna say it's a week, but it takes a while before like you can get radio communications from Mars back to Earth.
Oh, yeah.
The signal like
Okay.
covered that.
Should just do
Okay.
more stuff.
It says that a satellite moves in a stable orbit around the Earth with speed v0 at a distance r from the center of the planet. There's my satellite. For this satellite to move in a stable orbit out at 2r from the center of the planet, the speed of the satellite must be. So we're going to move it from here to here. Is that cool? All right. So this is a problem that takes a little bit of work, but it's not that hard to do. Okay. One of the things that we talked about was that if you're a satellite, you're in circular motion, so you know there's some centripetal force, right?
Yeah.
But what's causing that centripetal force? It's the gravitation from the planet. But you're not on the surface, so we gotta use Newton's law of universal gravitation. Is there a FG on your equation sheet?
Yes.
Okay.
After
Absolute
that.
value of Fg equals G M1 times M2 over R squared.
So this is the mass of one object, we'll call it the planet. This is the mass of the other object, the satellite. The R is the orbital radius, so it's the radius from the center, right? Not the altitude, it's the radius from the center. Okay? What's our centripetal force formula? Now, if you look at your equation sheet, there's no centripetal force formula on there. There's a centripetal acceleration on here, okay? Right?
Yeah.
There's centripetal acceleration, it's v squared over r, right?
You
But-
add M into that.
You gotta put the m in, so if you have the acceleration, since force is mass times acceleration, right? So I got a little mv squared over r. Now here's the thing, we're talking about the satellite, true?
Yeah.
So that's m2 in my equation? Is that cool? So can I cancel some stuff?
Yeah.
I got an R, I got an M2, I got one of the R's over here, I got the M2. So if I want to find the speed, I got GM over R. Does that make some sense?
Yeah.
Is that cool? Here's the problem. It's actually V is equal to the square root of GM over R, correct? Because I had speed squared.
Yes.
So what's gonna happen? I gotta double my R.
Yeah.
So if I double my R, really what's happening to the whole right side? Right? The whole right side decreases by a factor of root 2. So I'm going to say this one. Yes or no?
Yeah.
It's funny. I look back on the year, because I mean, we're really almost done. We're so close to being done. And I look back on the year and I just think, so many times we talked about, well, here's the relationship, and if this happens, what happens here? And if this happens, what happens here? Right? We talked about the coffee filters the other day, right? We were talking about the coffee filters. And I said, oh, well, the surface area, I'm talking about the speed changes with some constant over the square root of the surface area, right? So if you double the surface area, what happens to the speed? It's gonna go down by a factor of root 2. Same thing here, because we see, I mean, how often do we see things that are so similar? All the time. Like, we just see these things all the time. Hopefully you're starting to see them also, and you don't feel like we're just some disparate amount of topics that we never overlap or never relate. The mass of planet X is 1/10 the Earth, and its diameter is 1/2 the Earth. That's the acceleration due to gravity. Okay, so we've seen this before, but it's a slightly different style. So what's G on the Earth? It's equal to G, mass of the Earth, all over, radius of the Earth, squared. True?
Yes.
All right, so let's do planet X. What's the deal with planet X?
G.
We have 110 ME.
Oh gosh. Right? Now, this is actually kind of hard.
Oh, I just realized what I did wrong.
Okay, this is actually kind of hard because to kind of massage this thing, we got to figure out what's going on. Because basically, I have G, correct?
Yeah.
All right, what else is on top? Definitely ME,
Yeah.
correct? But the 10 is in the bottom, but I still have this R over 2 squared in the bottom, right? But the thing is that when you divide by a fraction, what are you really doing?
Multiply by just
Multiplying by the reciprocal. So this is G ME. We know we have the 10 in the bottom, right? But we're going to divide, which means we're going to multiply by the reciprocal, true? So this is what? R squared over 4, correct? And I'm going to multiply by the reciprocal. Well, that leaves the R squared in the bottom, but where does it put the 4?
on top.
On top. So now what I have, which is weird, is I have G ME all over RE squared, right, times 4 over 10.
Yeah, I did 1/2 R squared instead of R over 2 squared.
Yeah, right? So that's a thing, right? You're changing the R, but the R, the whole R value is squared. Okay. Anyway, if you then compare it to this, so our GE value here on Earth is about 10, and so then I gotta multiply by 4 over 10, and that's about 4. Cool?
Yeah.
But how many times in this little quiz have we seen this problem? I want to compare my new planet to the old planet. Is that cool? Now don't get me wrong. You may not see any gravitation problems on your AP test. It's a small portion of the test, right? But I want to make sure that, you know, click, cancel. How many are there? Jesus, what are we doing? Satellite X moves around Earth in circular orbit radius r. Oh, love this one. This one's fantastic. So, are these in circular orbit? Yes, they are. So if I start off with my circular orbit framework here, all right, so I got my satellite, it's cruising out here, right? There's the R, okay? So what do we know? What do we know about the centripetal force and the gravitational force? Are they equal?
Yes.
Sure, okay? So the planet has mass big M, the little satellite has mass little m. Sound good? So follow me along. I will tell you how to recognize this problem in a second, but just follow along with me for a moment. Okay. So if I do little m, what was that?
Loud sneeze.
Oh, okay. Is that cool? We just saw this a moment ago. Now, if you're going in a circle, how do you calculate the speed of something going in a circle, right? Don't you do like distance over time?
Yeah.
What do we call the distance around a circle?
Circumference.
Circumference. How do you calculate the circumference? So I also know that my speed is equal to 2 pi r, and what do we call the time it takes to go around once? That's the period, right? We were talking about period today in classes, the time it takes to do one oscillation. It's also the time it takes to do one revolution. Is that cool?
Yeah.
Okay. So do I have a V here? Do I have a V here?
Yes.
Okay, so if I have to square this one though, what's 2 squared?
4
What's pi squared?
pi squared,
R squared all over
d squared.
t squared. Now, if I set this v squared equal to this v squared, some magic happens. I end up with gm over r is equal to 4 pi squared r squared all over t squared. Now, interestingly enough, so often I try to cancel stuff. Can you cancel anything here? No, but I think you should collect all your r's together. Does that make sense? So I'm gonna move my t up here and move my r down here, and I end up with this. I end up with t squared over r cubed is equal to g, nope, it's equal to 4 pi squared all over gm. Is that cool?
Yeah.
Now, why do we care? How do we even know that this is a thing? So it says, satellite X moves around the Earth in a circular orbit. Satellite Y also moves around the Earth and completes one orbit for every 8 orbits of the Earth, or every 8 orbits completed by satellite X. Is that cool? Here's the deal. Is 4 a constant? To our knowledge. Is pi a constant?
Yeah.
Is g a constant?
Yeah.
Is m a constant? It is for this problem because both objects are circling the Earth. That means that the t squared to r cubed ratio is equal to some constant value.
Right.
Which is like the coolest thing, because now what we can do is just say, oh, well, if that's true, then I can say that t squared for x over r cubed for x has to be equal to what? T squared for y over r cubed for y. Everything that orbits the Earth has the same t squared over r cubed ratio. Also figured out by Kepler in the 1600s. What are we doing with our lives?
Yeah.
I wonder how old he was when we figured this out. They didn't live that long, so we couldn't have been that old. Definitely not in his 50s, like some yahoos. Anyway, let's see if we can figure this out. Now, how did I know to do this is the question. Okay, here's how I knew. Because the question asks you about 2 things. First of all, it says, what is the orbital radius of satellite Y? Which means I got to calculate an R at some point. Does that make sense? And then what information does this tell me over here? X does 1 orbit for every 8 orbits. You guys with me on that? Now, there's an actual problem with this problem that I don't love. I can never figure out which, the t for one is 8 times the t for the other. I just don't know which is which. Is it, and this is a real question, is it tx equals 8ty, or is it 8tx is equal to ty? So, satellite Y is also okay. Okay, so satellite Y is in circular orbit and completes 1 orbit for every 8 done by X. So X does 8 in the time that Y does 1. So if X is doing 8 in the time that Y does 1, it seems to me that X's period is smaller. It takes him less time.
So ty equals 8tx.
Ty equals 8tx. Yes, no, or maybe.
Yeah.
Is that cool? Now, can we substitute in? We can. Let's do it. So I have tx squared over rx cubed is equal to, now I'm going to substitute this in here, but don't make Charles' mistake. We got to substitute the whole thing. This is 8tx squared over ry cubed. Cool? You like it? Or no?
I don't,
That's fine. So let's go back. So we know that for each of them, the t squared over r cubed is the constant.
oh, okay.
So that means that since they're both equal to the same constant, I'm gonna set them equal to each other.
Okay, I get it.
So I have t squared x over r cubed x has to be equal to t squared for y over r cubed for y. Then, using our powers of reasoning, we decided that 8tx was equal to ty, and so I substituted that in for ty right here. Is that cool? That's how I ended up with that. Sound good? Now, what I find hard about this is we gotta solve for the radius, we gotta solve for ry. Does that make sense?
Yeah.
So if I do this, I end up with ry cubed is equal to, what's 8 squared? 64 tx squared times rx cubed all over tx squared. Is that okay? And what's interesting about this is on this side, my tx squareds cancel. So I'm left with ry cubed is equal to 64 rx cubed. And now what do I have to do with both sides? You gotta cube root them, right? So cube root gets rid of these guys. What's a cube root of 64?
4.
Ding, ding, ding. Still like extra paper on the AP test.
Yes.
I fit all of that in.
Don't they give you scratch paper?
I don't know.
Probably.
We haven't taken it.
Well, you've taken other AP tests.
Yeah.
Not math.
Yeah, but I didn't really.
What?
I
Not
guess-
math.
Grab
was
it.
I don't think we got extra paper in
I didn't
calc.
take him.
Oh, really?
Why?
I think there was just a lot of space.
That doesn't matter.
Oh, well, if there's a lot of space, there was a lot of space.
I feel like
Yeah,
there
there's
isn't
like
a lot of
there's
space.
a lot of space.
Yeah, it was like.
Yeah, Cal had a lot of room, so.
Perfect. All right, you guys got that?
I don't mean to interrupt, but I don't know if the low battery mode's gonna screw up your recording.
Oh. Low battery? It's not good. I don't even know if it's recording.
It says it's recording, so.
Perfect.
Here's a real question, is Keegan gonna watch it?
No, no one's gonna watch.
I don't know, he
Tommy
might.
would.
I know it works.
I think Keith is gonna watch it.
Yeah, he does.
Oh, I can't use this one. I need this one from here.
Yeah.
Yeah. Yeah. No, he's known that it's gonna probably.
What's going on?
The NFL draft is happening right now, actually downtown, which is pretty cool. But I figured my education is probably more important, so.
I know, my dad is there.
Well, I mean, here's the question.
You wanna go? Like, gravitation.
Do I wanna go? Do I wanna go?
The recording probably unpaused right at that point. It's 29 pick. Which reminds quarterback. Kool-Aid McKinnon. That would be so.
You think Joe's gonna watch it?
What? Oh, probably.
What do they have? They have like 8 minutes per
I think
pick.
Joe
They-
says.
Oh, it's 10.
Yeah, I don't know.
29?
How many kicks are there?
290. There's no one that, it's gotta be like incrementally less. Like they don't, like after a
Well, yeah,
while,
yeah,
they just start.
Most of the time, they're just.
All right, let's hope for the best. Okay. So that was hard, but now we know.
One of them drill a hole, put a script, just, oh, for the thing, I see.
Okay. Let's refer to a ball that is tossed straight up from the small spherical asteroid with no atmosphere. The ball rises to a height equal to the asteroid's radius, then falls straight down toward the surface of the asteroid. What force, if any, acted on the ball on its way up? So here's R. All right, here's R. when the ball's on its way up.
Gotta be decreased.
Only a decreasing force acts downward. Only an increasing gravitational force acts downward. Only a constant gravitational force acts downward. Both a constant gravitational force that acts downward and a decreasing force acts upward, like the force from the throw, or there's no forces on the ball at all.
Decrease.
So what's interesting is there's no atmosphere. There's a subset of people that think that the gravitational force on our planet is derived from the atmosphere on the planet. It is prevalent. It comes from this idea that we get taught in some junior level classes where, not junior as a high school student, but like low level classes where in your chemistry class, the teacher will tell you, oh, there's 14 pounds of pressure per square inch because of the atmosphere. Well, that's true, but that force is down and sideways and upward, right? But you think about the fact that the atmosphere is this huge thing pushing down on you, but that's not how fluids work, right? I mean, think about it. If that were true, then one, if I was in this room and I raised this up here, wouldn't there be more air below it and it would go up, right? That doesn't make any sense. Plus, you go to the moon, there's no atmosphere at all, and there's still gravitational force. So people, okay. Does the throw act on the ball after you let the ball go? No. Okay? So we're left with a constant gravitational force as it goes upward, an increasing gravitational force as it goes upward, and then a decreasing force as it goes upward. If we were at the surface of the Earth, what would we know about the gravitational force? It's constant. But where are we here? Like, this ball goes up to a height of radius r. Is it far enough off the surface that the gravitational field strength is decreased?
Yeah.
Yes, it is.
Well,
So, go
Isn't
ahead.
it technically, even if we were on the Earth, would we say that the force decreased?
We totally would. We totally would, right? But because we can't get off the surface in a way that's meaningful, I drew a picture the other day that said, well, when you're at the surface of the Earth, the gravitational field lines look like this. Oh, man. The gravitational field lines look like this, where they're equally spaced and point straight down. That implies a constant field, equally spaced. But when you get off the surface, what happens here? What do you notice about as you go off the surface? What happens to the spacing between the lines? The lines get farther spaced apart, which means your gravitational field is decreasing as you get off the surface. So I have a decreasing gravitational force.
That person needs to play Phys. That would go crazy. Go out the stadium.
No, I need to play baseball, dude. Like, they could fucking.
Oh my.
I left Dexter's baseball game to come here. It's fine. He plays a lot of baseball. Ooh. A satellite of mass m moves in a circular orbit of radius r with a constant speed v. True statement about the satellite includes which of the following? Man, I don't know. It's a great question. Okay, circular orbit. Let's put my satellite out here. So here's my satellite. Radius r, speed v. Mass m. Did I?
Yeah, I thought we were on pace.
Suck at life. Here we go. Its angular speed is v over r. Is that true? Isn't v is equal to omega r?
Yeah.
Is that true?
Yeah.
Yeah.
Like they just threw that kind of, like seems kind of random, but so that's probably true. That seems okay to me.
Yeah.
Is that cool?
Just threw it out there.
Its tangential acceleration is 0. So this is really interesting because if you look at this here, okay, does it have some centripetal acceleration?
Yeah.
It absolutely does. Can the centripetal acceleration speed it up or slow it down? It cannot. It cannot. If you want to speed up, your acceleration and velocity have to have some component in the same direction. Even if your acceleration was like this and your velocity was like this, you would be speeding up because there's a component in this direction. If you want them to slow down, what has to be true? There has to be some component opposite the velocity in order to get it to slow down. But what if you're perpendicular? Is there any components that are in the same direction or opposite? No. That's why the centripetal acceleration can't speed you up or slow you down. Does that make sense? But they're not asking about that. They're asking about the tangential acceleration. If you have tangential acceleration, right, that's tangent, right, it could either speed you up or slow you down. The way I drew it, it would say it's slowing down, right?
It's a constant speed.
So then that's true.
That has to be true.
I agree. Drew, great poll, right? He's like, but it can't have tangential acceleration because speed is constant.
So that only gives us one answer.
That's
The magnitude of the centripetal acceleration is constant. I think that's
Well,
true.
You could get 1, 2, and 3.
I only said that because there's no 1 and 2.
Okay,
So,
Charles,
yeah.
that's fine.
So I was just moving.
That's fine. Don't break the test. Cool? All right. I like that one. Did I skip one? Are you sure? I think we tossed the ball up.
It's a different question.
Oh, different one?
It's the
ball
same
question.
prompt, but different question.
Oh.
Oh.
Hey.
Context.
Wow, this changes everything.
What it was called
Was.
Okay. The acceleration of the ball at the top of its path is a maximum. What did we decide? If you're going to calculate the acceleration, it's g mass of the planet over the radius squared. So when you're at your maximum radius, what's true about your acceleration? It's the least.
Yeah.
Okay? Equal to, no. Equal to the accelerated surface? No. Equal to 1/2? Woo, 0. Okay? Trust me, there's a lot of kids out there that think when you throw a ball up and it gets to the top of its path, its velocity is 0. A lot of people think the acceleration is also 0. Is that true? No. If the velocity were 0 and the acceleration was 0, what would happen? It wouldn't go anywhere. So if it's 0 velocity, it has to have down, so not this one. Okay, smart people. What kind of relationship is this?
Inverse square.
Inverse square.
Gotta be 1.
It's 1/4, right? Do you see how these themes are just showing up again and again and again? That's why I ask you guys to do these practice multiple choices, because we just see the same thing over and over, and then the next time you see it on an actual assessment, you're like, God, I've seen that problem so many times. I hope so, right? I don't want you guys to be like, get to the test and be like, I've never seen anything like this before. That would break my heart.
I saw a question that
Oh my, how many are there?
20.
Jesus Lord.
Would you like stop at some point?
We can stop and do something else. Doesn't matter to me. You were saying, oh, this one's hard though. Charles, you were gonna say something?
I was gonna say, I saw a question earlier today. It was like a person was inside a hollow sphere at the center.
Mm-hmm.
Like, what's like the acceleration?
Sure. Well, the thing is, like, even on the planet, right? Even on the planet, if you were to somehow tunnel to the center, what's interesting is all the mass would be around you.
Yeah.
So the gravitational forces would balance, right? So the net force would be 0, your acceleration would be 0, right? One of the classic questions says, well, what if you took a planet and you drilled a hole through the center and then you just jumped in from one side? What would happen to you?
Oscillate.
You would, as a matter of fact, right? Because you'd speed up. Now, you would speed up a lot in the beginning, but as you got closer to the center, your actual acceleration would be less. Your speed would still be increasing, but your acceleration would be less and less. Because when you got to the center, your acceleration would be 0. But you're already an object in motion, so what's your tendency? Stay in motion, so you cross over the center. Now the acceleration is in the other direction, so you're slowing down, but who's your friend? Symmetry is your friend, so how far do you make it?
Right back to them.
Just to this other side. And if you don't step out, what are you gonna do?
Go right back.
How long would it take for air resistance to become a factor? Would that be instantaneous?
Yeah, so the air resistance would start slowing it down immediately. But we don't put air resistance into our, I just drilled a hole through the planet problem.
Just jump here. $5.
Would you eventually just be stuck in the middle?
Yes. Literally. So this is called damped harmonic motion. So we talked about harmonic motion earlier today, where if you have harmonic motion, okay, right, if you have harmonic motion, right, your amplitude stays constant. But if you have a force, like a resistive force, where there's air resistance or friction, what ends up happening is something like this. I'll start with a larger amplitude so you can see what I mean. You start with a large amplitude, but over time, what happens to your amplitude?
It looks eerily similar to the graph that Rosipos told us we're gonna have for our mood in Germany this summer.
What's really interesting about this is if you were to plot these, it's an exponential decay function,
Last week in June.
right? Yeah.
I'm going to Germany.
Okay. Let's skip 15, let's go to 16.
Mr. Paddock, I don't know if your phone is recording.
Uh-oh. Did it quit?
I don't know what that is. Maybe low storage?
Oh, looks like it's still trucking along. Look at, new planet, twice the radius, 5 times the mass. Have we seen this problem before?
Many times.
Many times.
Right? Dudes, come on.
Do you wanna do 15?
We're gonna come back to it, it's a hard one. Oh, look,
Oh, it's
have we seen this problem before? Yes, we have. Now, it says when the moon. Oh, so this is a great problem. So this is masquerading as a planetary problem, but what does it ask you for?
The moon.
The center of mass.
Ooh.
Okay. Do you guys remember how to calculate the center of mass?
Yes.
I actually think it's on the equation sheet. Is it not? Did I just make that up?
Yep, XCM, sum of MI,
Yeah, it's on.
XI, over the sum
Oh, yeah,
of
it is.
MI.
It's weird.
Now, you gotta realize what that says though. I'm not sure that's helping you, right? But if you wanna find the center of mass, you take M1 x1 plus M2 x2, all divided by what?
Yes.
Right? So, a moon of mass m orbits a planet of mass 49m in an elliptical orbit as shown above. When the moon is at point A, its distance from the center is RA and speed v0. When the moon is at point B, its speed is 5v0. When the moon is at point A, the distance from the moon to the center of mass, okay, so the distance from the moon to the center of mass of the planet moon system is most nearly.
They want you to find the other radius.
So what we're gonna do is we're going to look here. So when the planet is at A, okay? So what we have to do is, because we need to insert a distance here, we need to decide what your 0 point is. Where would you like to put your 0 point?
Center of the biggest thing.
That's totally fine. You could put it at the center of the biggest thing. You could put it at the other thing, you put it between them, but Nico said, let's put it here. Okay, so this is x equals 0, which I love. Is that cool?
Okay.
So let's do, which one do you want to call 1, which one do you want to call 2?
A called 1.
So you want to call the moon is 1?
Yeah.
Okay, that's fine. So x center of mass is equal to m, and then what's its distance from here? RA plus 49m times what?
RB?
It is not, because we are actually looking for,
Where's our center? Oh, 0.
so we decided that the center of the planet was our 0.
Yes.
So when we took this first x, it was the distance from our 0 to the planet when it's at A. So then what is our x2 then? 0.
Fantastic.
Over what?
Something else.
Is that cool? So the position of the center of mass is going to be equal to MRA over 50M. Okay? Now, that is the answer. I'm sorry, that is what we solve for, but we really need to ask, we got to figure out what the question is asking.
The moon, planet moon system.
So, given my two things here, my planet here and my planet at, or my moon at A, this is my 0. Where's the center of mass? It's here, because what I solved for was this, which is 1/50th RA. You with me? But the question says, when the moon is at point A, the distance from the moon to the center of mass of the planet, moon system, is most nearly. Well, what is this distance then?
40.
I think it's 49/50ths. Is that an answer?
That is an answer.
Is that the answer? Look, there it is. I just freaked out for a second.
Oh, because it said the distance from the moon.
Exactly. I found that a little bit hard because you had to do two things here. You had to correctly calculate, and then you had to like reinterpret the problem. Yes?
So do they just throw in like that point B on there to trip you up, or is that?
No, this is going to be the stem for 3 problems.
Okay, that makes more sense.
Oh.
Okay?
It's not giving you the gravitation.
The next thing they're going to ask you is, oh, well, if it's going 5 times faster here than here, compare RA and RB.
Okay, that makes sense.
What problem is that? We did that one earlier. What problem is that?
Angular momentum.
That's the angular momentum problem,
Got it.
right? And then they're probably also going to ask how the force at A compares to the force at B, right? And since it's 5 times farther away, how does the force here compare to the force here? It's 1/25, because remember, the force, the gravitational force, is equal to G M all over R squared. So if you go twice as far away, it's 1/4 the force. If you go 5 times as far away, it's 1/25 the force. Okay? All right, let's check that. Okay, so that was that one. What number was that? That was 18.
That was
17.
That was 17?
Whoa, would you look at that? Predicting the problem, that's crazy. I heard that too.
This one says, when the moon is at point B, the distance from the moon to the center of the planet is most. Oh, yeah. Yeah. So, when you have L1 has to equal L, well, this case it's A and B, right? So you have R, A, M, A, V, A is equal to R, B, M, V, B. Okay. What's the last one? Oh, it's the escape velocity? Stop. Stupid. Care about escape velocity. This is a hard problem. Like, I actually think this is a hard problem. two identical stars, a fixed distance apart, d, revolve around in a circle about their mutual center of mass as shown. Each star has a mass m and speed v. G is the universal gravitational constant, which the following is the correct relationship. So if two stars are orbiting each other, right, they don't really orbit each other, they both orbit the center of mass, which is true for anything. When we had this planet moon system over here, right, we say, oh, this is going around, the moon is going around the planet. But that's not actually true. Like, because they're pulling equally on each other, but because this is so much larger, the center of mass of the Earth-Moon system is inside the Earth. Or whether it's a Earth-Moon or it's Sun-planet, it doesn't matter. It's inside the central object. So that means the central object doesn't actually rotate. It might wobble a little bit, right? It might wobble a little bit, but it doesn't actually rotate. But what happens if you start increasing the mass of this one and making it larger and larger? What happens to the center of mass? It starts moving this way. Well, now all of a sudden, what's going to happen? This one has to orbit around the center of mass. This one also has to orbit around the center of mass. So they actually look like they're orbiting each other, but they're actually just orbiting the center of mass. And what happens if they have the same mass? Well, then they're just going around each in the same circle. Does that make sense? Yeah.
Is the center mass like the focus of, like, how
That is a great question. If they're orbiting each other, is the center of mass at one of the focal points? My instinct is to say yes, but I would need to think more about it. I am almost out of gas, though. Bring a kid to work day was a lie. All right, so what do we know? Are these guys in circular motion?
Yes.
They totally are. What's causing them to be in circular motion? The gravitational force. True? Sound good? So, what's the gravitational force formula?
G M over R.
And the centripetal force formula? Okay. Now, this is the problem. Because in every other problem that we've done, we've been able to cancel some R's. But here's the problem. The R value is here, correct? But this R isn't this R. Because what's pulling on the other thing? The other star. So what is this value then? And what are you going to do there? See how annoying that was? So this is a problem designed really to kind of trick you into going like, oh, I know the algorithm I used to set these two things equal, but you really have to take a step back. Yeah?
Just to clarify, those two M's, normally one would be, they'd be different, but because they're the same, it's, okay. I just wanna
Exactly.
make sure I was-
And what's nice is one of them is going to cancel anyway.
Yeah.
True? So now I have v squared over r on the left side is equal to gm over 4r squared on the right side. V squared is equal to gm over 4r. And v is equal to, this is dumb. Oh, it's v squared, good. Perfect. Uh-oh,
Uh-oh.
that's not an answer. Oh, yes it is. Because they have it in terms of what? They have it in terms of D.
What is D?
D is the
Oh, the fixed distance.
the diameter distance.
So 2D, so.
It'll be 2D. Cool.
Okay. All right. That's a hard one. We're gonna go back to the very first problem. So, for those of you who missed the first couple moments, we have our planet. Okay, and we have a satellite out here. And the satellite is in circular orbit. Cool, or an orbit of some sort, right? And the question was, if F1 is the magnitude of the force exerted by the Earth on the satellite, and F2 is the magnitude of the force exerted by the satellite on the Earth, how do these two things compare? What do you know for sure? They're Newton's third law force pairs. They have to be equal. There was some confusion in the audience at the beginning. Okay? But is this a gravitational force? This is a gravitational force, true? So if I actually just want to calculate the gravitational force, what's my gravitational force formula? G, M1, M2, all over d squared or r squared, right? That's the distance, right? Well, here's the thing. This equation implies Newton's third law force pairs, doesn't it? Like it does, because if I look, G is a constant. In this case, the D is just the D, it's the distance. So I'm comparing M1 times M2 to M2 times M1. And what do you know about that? They have to be the same. Multiplication is commutative, right? So what I love about this is Newton's law of universal gravitation, again, 1600s, really does imply that the force that one on two, or force that one exerts on two, has to be the same as the force that two exerts on one. That blows me away. Like, that blows me away. Okay. All right, I'm done. Are you guys good? Okay. I thought that was really fun. Did you guys, do you feel like enlightened? Do you feel like, oh, that makes some sense, or no? Worth your time? I know it's a big commitment. I know it's a big commitment, but.
Kind of. I worked on